everybody, and welcome to the 75th video on my channel. And yes, I know this looks a little bit different because I am trying something new for today and probably the next few videos. Now, I'd really like you to go in the comment section and see which one is better for you, whether you like the Microsoft Whiteboard or you like this, which is using Google Slides and other softwares. So without further ado, let's move on to the actual topic of this video. This video is about an introduction to differential calculus. Now, in my last video, I talked about differential calculus and integral calculus. Now, we're going to hold just a bit more on differential calculus, and after that, we're going to start doing limits. Now, the derivative is a bit different. Now, if you look at the bottom, there's something called the formal definition. F dash x is equal to limit as h approaches 0 of f of x plus h minus f of x all over h. Now, I would not really worry about that right now because you haven't even been exposed to limits, unless you have earlier. But if I'm assuming you've probably not been exposed to limits, so I really don't think you should do that. So if we look at the concept of the geometric interpretation, it's quite accurate. The derivative, it measures the instantaneous rate at which a function's value changes with respect to its input variable. So if you have a line, let's say the line over here, the one that I'm circling with my cursor, if you have that, if you see the rate of the instantaneous change, so maybe at this point over here, a line, something like this, might have a slight positive rate of change, but at a point like here, it might have a negative rate of change. Now, as I said in my last video, there is a formula for that, which is calculated by many different rules, which we're about to cover. And then the geometric interpretation, it is the tangent line. Now, a tangent line only intersects the graph once. So that's really about it, and then the notation we also covered last video. Our next rule is the power rule. This is probably the first rule that you're going to learn in any calculus course, and I think it's quite necessary for anyone to know, even in an introduction to calculus. The basic rule says, for any real number n, if f of x is equal to x to the power of n, then its derivative is f of x is equal to n times x to the power of n minus 1. Let's explain that a little more. Let's say we have f of x is equal to x squared. Then the derivative f dash x is equal to n, which is 2 in this case, so 2 times x to the power of 2 minus 1, which is 1. So f dash of x squared is equal to 2x. Now, the reason this is important is because this is pretty much the groundwork rule, and it's used in combination with a lot of other rules. Another sub-rule is the constant multiple. If we have a constant, let's say c, times another function, which here is u of x, but you can say g of x, h of x, I of x, it doesn't really matter, it's just dummy variables, then the derivative of x is equal to the constant times if you took the derivative of the other function. So if we have the constant c equal to 3 and u of x equal to x squared, that would be 6x, because 3 times 2x is equal to 6x. Now over here it's an example, so if you have d over dx of a function, this is also another way to represent the derivative of a function. Instead y, you write out the full function, and the rest of the steps are shown over here. Now, fractional powers are a little bit different, but they follow the same basic formula, where you have if 1 over 2 is equal to n, then you'd have n times x to the power of n minus 1. Now, sometimes it can go on the denominator because it's a fractional power and it could be less than 1. The next basic concepts are the derivatives of the trigonometric functions. So, this handy table shows all the derivatives. If we have sine x, the derivative is cosine x. Cosine x derivative is negative sine x. Tangent of x is equal to secant squared x, not secant 2x. Cotangent of x is equal to negative cosecant square x. The derivative of secant x is secant x tan x, and cosecant x is equal to minus cosecant x cotangent. For this, I think copying down this table is very useful, as well as copying down this rule in the constant multiple rule. So if you really want to take away two main things from this video, it would honestly just be these two things, because these are the most basic, the most groundwork videos that you can find. To the next, which is the product rule. Now the product rule is if we have a function h of x, which is equal to f of x times g of x, that means the derivative of h of x is the derivative of f of x times the derivative of g of x plus the derivative of plus f of x times the derivative of g of x. That's basically all the rule is, and this is also a pretty groundwork rule, but it is a little more complicated, and it's honestly quite used along with this conjunction rule, the quotient rule, and also the chain rule, which I'm going to cover soon. And you could look at the example, but if you're not completely sure and you don't really understand the previous two slides, you can always go back to that. Quotient rule is kind of the exact opposite. If you have h of x is equal to f of x divided by g of x, there's a different rule. So, if you have h of x is equal to f dash of x, or the derivative of f of x, times g of x minus f of x times the derivative of g of x, divided by g of x whole squared. It's not the entire expression squared, it's just g of x squared. So that's really all there is to it for the quotient rule. And as you can see, this is significantly more complicated than the first two rules I covered. And as you see, calculate, substitute, derivative, simplify, it's basically the exact same thing. And as you can see, it's already much more complicated, especially with the expression. But don't worry, it's not too complicated. It's just a lot of symbols and numbers. But it's definitely a harder concept to understand than the other more easier concepts like the product rule, the trigonometric functions, and the power rule. Going on to another rule, which is the chain rule. What happens here is there's 4 steps to really solving a problem, like this. The first step is to identify the composition. H of x is equal to f of g of x. This is the first step. The second step is to apply the rule. Now this rule is become h dash of x is equal to f dash g of x times g dash of x. Now this is saying if we have a function f of g of x. So let's say instead of x squared we have x minus 1 squared. So f of x would be equal to x squared, but g of x is equal to x minus 1. So f of g of x, or h of x, is equal to x minus 1 whole squared. Now, the third step in this process is to substitute, which is to replace this general rule with specific functions. So, and the fourth step is to simplify. For example, for h of x is equal to sine of x squared, h dash of x is equal to cosine of x squared times 2x. If you look at the first two slides, which was the power rule and the trigonometric function rule, that'll actually also show you how you can use that. And it's quite simple when you really realize what the main key points are. This slide will be higher order derivatives. What we mean by that is the second derivative, the third derivative, and so on. All the derivatives we've been covering so far are first derivatives, which, if you look at the first slide, it's the instantaneous rate at which a function's value changes with respect to its input variable, or the instantaneous rate of change. So that's what the first derivative is. Now, the second derivative is a bit different. Let's say, instead of having the first derivative as the derivative or a function, we graph that. And then we calculate the instantaneous rate of change for that. that would become the second derivative. Now for higher derivatives, we're just going to have to continue the process again and again and again until we realize the required derivatives. Now if we wanted to figure this out algebraically, we'd just differentiate it using the rules shown before, and then differentiate it again for the second derivative, and so on for the third, fourth, and final rule I want to talk about is implicit differentiation. Everything we've discussed so far is just in relation to x, where we've had f of x is equal to some function of x. But what if we had xy? What if we had a function like xy is equal to y squared minus x squared plus 3? Now for that, it would be hard to really substitute and solve for just y. So what we have to do is apply something called implicit differentiation, which also uses the chain rule. So what we have to do first is apply d over dx to both sides, or d over dy if you want to do it in terms of y. Now, for the y terms, we'll have to apply the chain rule, which is shown right over here. D over dx of y to the nth power is equal to n times y to the n minus 1 power times dy over dx. Now, what we have to do is we have to make all of the sides one side with all terms which have dy over dx, because that's what we're ultimately trying to solve for. Then we can isolate it algebraically just like we would do any other variable or function. So on the bottom, it's a quick example. If you want to try figuring it out on your own, that would be a good challenge. So, thank you so much for watching this video. See you in the next one, and bye-bye.